Good morning all. Welcome to today's webinar. I hope I am audible. Today we have a topic number 6. Sorry, I have an... Excellent. Thank you very much for letting me know I can be heard. Today we have a topic number 6. Last time we asked the question, is it possible? And the response today is, it is not. Welcome to our series of breakfasts with measurement system analysis. Today it will be the first time when we'll touch the part on the measurement process, as we have concluded the measurement system the last time. And I will share my favorite whiteboard to make my point. All right, the measurement process, similar to measurement system, we can do two approaches, one with experiment and one without. The one without the experiment, with the type B uncertainties, we'll cover in one of the future webinars. But already I'm inclined to say that the measurement process is almost impossible without an experiment or without a prior knowledge which is coming from an experiment. So the experiment is the more important one. If we say that we do experiment, that it is yes to experiment, that's the same as saying that we are going through the uncertainty type A. This is a reminder about what we already said. The type A and type B uncertainty is not related to the type of the uncertainty. It's only related to the way we get it known. So type A, that's from experiment. And an experiment for a measuring process has always 3 parts. 3. And when I say always, I mean their standard. Of course, there can be any experiment that you need to do, but since we are dealing with the industrial environment, we want to have things standardized so that they are easier to evaluate, that we know what to expect when we do some calculation on it. So the standardized experiment has 3 parts. It always includes the repeatability in the first place, and we already had a repeatability. It was the standard deviation is denoted by U. The repeatability was for EV, that's for equipment variation. And we had a reference in the measurement system. Now we get rid of this R and substitute it with an O for an object. And that's slightly different thing. We expect the measurement device would be slightly less repeatable, would have a bigger span of uncertainty in repeatability when dealing with an object rather than with the reference. The second part of the experiment is coming from the parts. That's exactly this object. And this is the representation of the production process which produces the parts that we measure with our measuring device. And again, I need to remind you that we are dealing with the compatibility of the measuring device with the production process. Any qualification of a measuring device that we do here is only related to the production environment. And that's throughout the whole series of webinars that we have. It is a specific application, but the one in which we can do certain simplifications here and there. The variation of parts is not denoted by U, it's denoted by S. It is a standard deviation, but it is not measurement uncertainty. The way the parts are different should not be influencing the uncertainty of the measuring device. It does in some way, but we do not want to have it part of the evaluation. That was the second part. The third part is another important factor, another influence. Here I have to say one thing. One of the results of too much standardization through MSA was that it made most people believe that the most important influence is the operator, or as it's being called, the appraiser, which may not be always the case. So what is usually called the reproducibility in the measuring device does not have to be the appraiser. It should be the other big effect aside from repeatability. So what these effects may be? If the measurement system is built of several gauges, that's usually when there is a measurement operation with a measuring device which is not of a sufficient capacity, and we need to multiply the measuring gauges, then the difference between these gauges, as they all are being used to control the production process, is usually the biggest difference, and it is usually bigger than the operator influence. So that may be the other one. Then, of course, some of the uncertainty is coming from the measured part itself. And how to imagine that? Let's say that we are measuring a diameter like this, and we all know what a diameter in real life looks like. A circle like this. So what is the diameter of a circle like that? It can be anything between this and this, and it really depends on the definition of the measured parameter. And since any measured parameter is burdened by its shape, then no matter what is the definition, there can be a variation coming in with the part. Of course, there are ways to limit that to a certain point, like calculating the average diameter. But if we care about the max-min, it usually is a big factor, a thing to consider. Another point may be the stability. This is how the measuring device performs morning, noon, and evening, and spring and summer and autumn, and in any other influence that is distributed over time. And this is a thing which is not really easy to experiment with. The experiment then takes a whole year. But it's certainly something to consider. If the variation, if let's say the systematic error changes just slightly over time, it's part of the uncertainty, no question about that. And then there is the temperature. It's a long time tradition in metrology to regard temperature as the important factor. It's not always so, but many times if we go to tiny little tolerances, it suddenly can play its role. Very good. So the first thing that we need to do is to decide what this factor is and build the experiment around this factor. How it is done. The experiment has a form of, let's call it a table, where there are parts. That's the variation that we want to take out of uncertainty. But we want to see how the measuring device performs with different parts. And then there is repetition. Each part needs to be measured a few times. And this already creates a two-dimensional table, the parts and the repetition. And this experiment with the parts and the repetition, we want to do at the different levels of the main factor that we have. So if the main factor is a person, if it is the operator, or as it's being called, the appraiser, we want to have this table done by operator A, B, C, D, whatever the number we'll choose. If this is a temperature, then these tables would be acquired at different temperatures. If this is the gauge variation, the comparability between the gauges, these should be tables generated with different gauges. So really, we are building up a 3D table, three-dimensional table. So how this table is being acquired? We have three ways to do this. We can be very orderly, make this 3D table with the, let's call it, operators or measuring devices A, B, C, repetition 1, 2, 1, 2, 1, 2, and then fill it in one by one, putting in the numbers. But there is a certain problem with that. If we analyze such data, we need to make some assumptions about the quality of how these data were acquired. And one of these assumptions is the assumption of independency, that each of the measured value is not dependent on the other, as it is in the real measurement process when it measures the production. We really don't know, and it is a work of randomness, what was the part before the one which we are actually measuring. And there is an interaction, there is an influence between the measured part and what was there before in the measuring device. So statistically speaking, the ideal case would be to collect these values randomly. Well, I like randomness and I like chaos, but it's not practical always. Specifically with these experiments, calling in different people or switching the measuring devices, not talking about switching the temperatures or the points in time, that's almost impossible. And even if it is possible, it's mostly impractical. So the way out of that is to make it smart, to randomize just parts of this table, to keep some level of order, but to make sure that the values are independent from each other. And the way to do that is, on the first place, to do the repeatability, the repetition 1 and 2 or more, whatever it may be. That would be the top layer. Then the main influence being it the temperature or point in time or an operator, which already can be in random order, and then the parts, and they will always be in random order. And in Yarvin, we did our best to facilitate that. And let's welcome Martin to our session. Good morning. And Martin will now show you how this is being done in Yarvin and how you can prepare your design of experiments sheet over there. Martin, over to you.
Good morning. So for this example, I just prepared a short experiment, short validation act, where I have two characteristics. For this showcase, it's only two of them, some diameter 1 and diameter 2. What's important in this case is to choose what's the greatest influence factor, and according this, the experiment table is designed. We have the most common factors that Jaroslav spoke about: operator, measurement system, object, stability or reproducibility over time, some other component, temperature, and one special here, and that's no influence. In this case, if you're choosing now, it's something you know from MSA as type 3 study. Yeah, so there is only one level. But this is not our case. I will stay with the standard operators for this showcase. And here I do just clear the data. And the first, what you have to do is to select how many repetitions, how many levels, and how many parts you will have in your experiment. This is completely up to you. You can go with from the simple experiment 3 to big experiments like I have here. And you can select the table, how the table is constructed. For example, the standard, what's the definition from the design of experiments is that the table is completely random. You can see that I have the operators in the random order. The parts are in the random order, and if I for each repetition. So this is quite unpractical because in not every time you can have the levels of the experiment in this randomness. So for this case, we have the second state, that is smart random, and here you can see that the levels, the main factors are ordered. We have one operator, second operator, third operator. If this is temperature, we can it will be temperature 1, temperature 2, temperature 3, and it will be much more easier to perform this experiment. And last is completely ordered, when everything is in order. One operator and the parts from 1 to 10. Yeah, so this is the three types of design tables you can have, from the completely random, every operator and every level is randomness, or smart random, levels are ordered and parts are in random. What's important here is that if you have a big experiment, for example, this 3 repetitions, 3 levels, and 10 parts, it you have to done 90 measurements. And if you have, for example, some bigger parts with lots of characteristics, it can be quite complicated just to prepare this table to be able to evaluate this. And for this purpose, we have something that can quite help with this sorting or with this creating of this table. You can export a PDF with some codes that you have a reader for. For example, I have mine for barcodes, and this is just the table or just the set of barcodes for every combination that is in the table. So what repetition, what operator, what part, and QR code, or in this case, barcode. And if you are doing your measurements, for example, on the 3D machine, the only thing you need to do is to some field to scan this code, and according this code, when you upload the data, the upload will recognize to what place the value belongs, and is so that means that the table is uploaded directly how it should be. What are the parts? What are the levels? So this can help quite a lot to save your time, and it doesn't matter what key fields you will use, because the upload will recognize it anywhere. I will just switch to some examples we have from our for our validation, and in this case it's the comparison of two measurement systems. You can see there is lots of parameters. I have done two repetitions, 2 levels, and 10 parts. And my experiment is completely done. I have everything I need, and now we can go back to results, and we have some overview of our evaluation. And now it's time to decide what's wrong, and that is something that will Jaroslav show us.
Thank you very much. So now we have landed with a bunch of values from this experiment. And these values, as it is right now on the screen, is divided into subcategories. So let's take a top view look of what's being done here. So we have the experiment acquired in whichever way, but to make it work, to be able to evaluate it, we need to put everything in order. And as Martin said, Jarvin can facilitate that in the way that you would be scanning the codes, or you would be putting in the data per the DOE plan. And first thing which is done is that all the values are put on one pile. So if we have 2 operators, 2 repetitions, 10 parts, that's 40 values. So they all are put on one pile, and we calculate their standard deviation. This is called the total variation. And in the measurement uncertainty, we make the assumption that the measurement error has a mean value of 0. That is an assumption, even for bias and things like that. It has a normal distribution, so we are left only with one parameter, and that's the standard deviation, or as we call it, standard uncertainty in this context. So we need to divide this one pile into subparts. The biggest part of this file should be the part variation. So that's one thing which is taken out. And something remains. And we expect that there will be certain portion of that pile coming from the main influence, the operator or the temperature or the gauge comparison. So that would be the other portion. And then there may be an interaction between the part and the main influence. And this is the mathematical model which is behind the analysis of this big pile of numbers. It's called the analysis of variation, or ANOVA. There are, in fact, two possibilities to do that. It's either the ANOVA or what's called the RNM, average and range method. And this is something I don't at all recommend to use. Because it is very imprecise. It is a way to do that, but very imprecise way, which only was practical at the time people only had a pencil and paper. That would be the adequate context to do the RMM. So please don't do that. Always go through the analysis of variance. So the mathematical model divides the big pile into the part variation, the main influence, and the interaction. And usually that is not all. Something remains. There still is some variation. And what remains is the equipment variation. That's a random variation which is not explained by any of the three factors. So what remains is the repeatability. And then we want to get rid of the part variation. We don't need that in the uncertainty. And we need to work with anything what is down here. The main influence and the interaction can be combined into the reproducibility. That is the reproducibility. What is below the line, what remains is the repeatability, and these two combined put together what's being called the gauge RNR, which is the uncertainty coming from the measurement process experiment. So this is the top level overview of what's being done with the data. This is something what is done in the background. We don't need to do that manually as long as we fill the tables correctly. So the software knows how to work with that. Very good. That concludes the topic today. Do we have any questions? I don't think so. And there is nothing in the chat. So if you do have questions, don't hesitate to contact us. We'll either respond to your emails. There is a question. Milton, please go ahead. The question is, this is for gauge RR study. But what about the other MSA studies? Well, this is an experiment on the part variation and one factor and its evaluation, an experiment which is done for measurement process. There is a non-replicable studies. Does the software has the ability for bias, linearity, stability? Of course it does, and this is something what we have already covered in the previous webinars. We have specifically covered the bias, the linearity. The stability is a part of the measurement process, which we will be covering in one of the future webinars. Non-replicable studies, that's also part of this question. It is a very special case where it is not possible to do repeated experiments. So one part of this cannot be done, but there are ways to circumnavigate that. And this is also something which we will be covering in the future. What about destructive test? This is exactly the case where it is not possible to do replications, where it is not possible to do repeatabilities. It's not part of today's webinar. We will be covering that in the future. Very good. Well, thank you very much for these questions. We'll make sure it will get in. Jan has shared the link for the videos, and if there are no other questions, no other comments, then I thank you very much. I wish you pleasant Christmas, and I am looking forward for the next one, when we'll be talking about the B-type uncertainties in the measurement process. Goodbye.
We are here to make it run. We are here to have some fun. We are here to work real hard. We are here to make you smart. Deribet, we are deribet. Deribet, we are deribet. Deribet, we are deribet. We are deribet.